Welcome back on the Introduction to ML and AI using Python for Mechanical Aspirants, and this would be some part of the continuation of week 11. Okay, so as we have discussed yesterday that our plot was not working, if I'm not wrong, so I have figured out after the class why it was not working. So there were some errors. There are a few syntaxes, a few lines which actually works in Jupyter but do not work in a similar way when you do it on Visual Studio Code. So if you remember, we had an iris data set and then we have used PCA on that, and then we had used two components, principal components, and then we ran this command by which we came to know that this two component had the information variation of the data set of with more than 95%. And then this was the syntax which was not running, so I have rectified it. So let's see what happens now after running this. I wanted to show you this. What I have done in fact was yesterday here there was some syntax problem and I had done a small mistake. Yesterday I have written the flower names here, Setosa, Virginica, and the third one, I'm not sure. So I've written those names, that was a reason. But if I see here, the target names what we have are 0, 1, 2. So that's the reason I've converted this target's name as 0, 1, 2. And then I'm running it again. So what you would notice is this plot, and this is what I wanted to explain here. So this is PC1, this is PC2. Now, things which we have to remember was we had 4 features: sepal length, sepal width, petal length, petal width. Out of that, we have converted those 4 features into new 4 features using PCA, PC1, PC2, PC3, PC4. And we have chosen only 2, and we have looked into the variation component also, that these 2 cumulatively had information of around 95%, as we also can see here, 72.9 plus 22.8%. So now if you notice here, what I'm trying to show is 0 is Setosa and 1, what is 1? So let me print this to understand what was 1. Let's close this and then run it again. Yeah, so there would be a name here now, target names, which I wanted to see. We have printed the target names, but it has to be somewhere. Let's see, where is it? Target names. Yeah, so Setosa, Versicolor, and Virginica. So that was I was not able to recollect Versicolor. So it's 0, 1, 2 in our case, because we are using, instead of using target underscores names, we are using targets, which has converted Setosa to 0, Versicolor to 1, and Virginica to 2. If you want, you can convert this legends from 0, 1 to 2, Versicolor, Setosa, Versicolor, and Virginica. Okay. So now, if you notice what we are seeing here, this is our class 0, this is our class 1, this is our class 2. Now, if you notice, with these 2 components also, we are able to segregate our classes with quite good efficiency. What do I mean by that? See, I can segregate this. If I want to use any logistic regression or anything else, say any hyperplane or anything, I can quickly segregate this 0, 1, 2 quite easily, because you can notice that there are no mixes with red color, mixes of red color with green and blue. So Setosa are it's quite easy to classify. But if you notice green and blue, which are Versicolor and Virginica, there might be a chance when you perform your prediction algorithm here, you might encounter 1 or 2 misclassifications. And when you do your original logistic regression on your 4 original input features, you can also observe what is the accuracy in that case, what is the confusion matrix which you would create, and what would be the final result in that case. And when you do with PC1 and PC2, you can also observe that. So let's try doing that. So what I wanted to do, yesterday's code is still not running because this SK learns this version what I have, and the version in which this runs are quite different. So I'll take this same data set and then let's see what is the accuracy which we are getting. Okay, so let's use this first. So what I'm doing here is I'm splitting the data, right? And if I'm not wrong, we have already done this in one of our models. So in SVM, we have done the same thing. Remember guys, we have used the same data set, right? So let's do one thing and let's split the data again into our PCA analysis. So let's split the data. X train, X test, Y train, Y test. And then instead of X and Y, what we have here, df underscore standard. Let's take the original data set first. Okay, df underscores X underscore standard. And then df underscores Y underscores standard. Okay, let's take 20% of it in test. Okay, makes sense. Now what we have to do, if I'm not wrong, now we have to import logistic regression or linear models, right? From Skill-Lync import linear models. Okay, and now from Skill-Lync we are importing linear model, and then we have to assign this logistic regression to some variable, right? Linear model dot logistic regression. Okay, and then we have to fit this, right? So where is our logistic regression code? Let's copy directly from there, which we have already done in our earlier sessions. So instead of doing all this thing again, let's copy it from here. So let's go back to our PCA and then let's run our logistic regression. Okay, so what I'm doing, I'm assigning this to some variable CLF underscores multi, this logistic regression, and then I'm fitting this on X train and Y train, and then I'm predicting the score for X test and Y test. Let's not use this for the time being. Okay, this makes sense to me. I think it should run. Let's see what happens. First, I have to close this graph, otherwise I won't be able to run this in Python code. Again, this graph has opened because I have to comment this, because we have already understood this graph using PC1 and PC2. Now it is throwing some error. df underscores Y underscore standard is not defined. So yes, we have not come up with any df underscores Y underscore standard, right? Y was directly df underscores Y. So let's directly take that df underscores Y, because those are targets, right? 0, 1, 2. So now let's run this again. Neither name nor data underscores ID are provided. Yeah, so these are all warnings. You can neglect it. But what we need to understand is the score. The score is 93.3%, right? And then let's do the same thing using principal component analysis. Okay, so before doing principal component, before running the same thing on principal component analysis, are there any doubts? Because I think it's 5, and then so as we have already seen the accuracy with logistic regression with original data sets, where we had sepal length, sepal width, petal length as the features, the accuracy is around 0.933. So now, to clear yesterday's doubt, how does it affect to our accuracy? Let's do the same thing with PC1 and PC2. Okay, now let's run the same thing on, let's change the variable name by say underscores 1, or let's say new name as say PCA, new variable PCA, okay. And this time what we would do is, let's comment this, the previous syntaxes, otherwise this will throw error, because it is X train and Y train are using the same thing from the train test split, right? So we have to log this, we have to comment this, and here instead of X and Y, we have to use our data sets which had PC1, PC2, and so this was our X where we had only PC1 and PC2, remember? So let's copy that for our X, and for Y we had final DF, right? So let's use this Y, and in this we have a column by name target. It's target, right? Yes. So we can live with this now, and then let's try the same thing here. Let's see what would be the accuracy, but it should be dot, that's the reason it is giving error. Okay, dot target, right? So this data frame has only PC1 and PC2. This was our final data frame where we have concatenated PC1, PC2 with the targets. So that's the reason now what we are doing is, instead of putting the original data set input features, now we are putting modified input features which are PC1 and PC2. And then this is our final data frame where we had concatenated target, and then we are only using target for our Y variable. Okay. Now let's see how does it work. So now if you notice, the accuracy is 0.9. Now let's do one more thing. So what we have done, we have only used PC1 and PC2, right? Now let's use PC3 also. Let's try that. There is no harm in trying. So let's try that as well. PC3, and let's see what happens now. So now, as I was telling yesterday, now we had only PC1, PC2 and PC3, and then the accuracy what we are getting was equal to the accuracy what we had with the original data set, right? That means the PC4 had almost negligible information carried by that, and we have already seen that yesterday it was around 0.5%, because this all three PC1, PC2 and PC3 is carrying 99.5% of information, and with that still we are able to come up with the same accuracy, right? So that was the whole point which I was mentioning yesterday. The accuracy might be equal if you are able to, if you are removing one of the features, say PC, like the one which has very least information in principal components. But then of course, if I remove PC3, then our accuracy was going down, as you have already seen. Now let's use only PC1. Okay. Now what do you think? What could be the answer? As expected, the accuracy should further go down, right? With PC1 and PC2, we had the accuracy of around 0.9. So let's try with only one principal component which had information of around 72.9%, right? So let's try this and check what happens. And you have note, okay, so now we had only PC1 where it is carrying only 73% of the data, right? But then if you notice, the accuracy is still not down. We have expected the accuracy should go down, and that was the thing, that was the assumption which we had yesterday, right? So that was the reason I told it's not necessary that accuracy should be dependent on your principal components. The reason why your accuracy is not going down is because the PC1 had all the information which might be sufficient to determine your output. Okay, that was the reason the PC1 we are getting quite good accuracy, but it's not necessary. It depends on the data set. Here our data set is very simple, and PC1 is quite sufficient to give us the solution with same accuracy, but we are only looking at accuracy here. Yes, you're right. you have got a point here. Why is it? It is because even though the variation of the data, what is that variation of the data means? It is variation of the input data, right? You had x1, x2, x3, x4 initially. Now you are coming with PC1, PC2, PC3, PC4. Even though we are capturing 95% of the information or the variation of the data using PC1 and PC2, but then the accuracy is decreasing with PC1 and PC2, but it was almost same with only PC1. That means PC1 was alone sufficient in terms of coming up with a good prediction rather than having PC1 and PC2. But amount of information carried only with respect to inputs. Okay, PCA works only on input features, right? That's the reason PC1, we are calculating PC1, PC2, PC3 and PC4 and tells that the variation of the data is captured in this principal components only of the input features. But we never tell how does it influence your predictions. PC1 is never used for better predictions or lowering down your predictions. It just captures less variation of the data and it reduces your computational time. That is why we use PCA. And that was the reason when you have asked this question, I was quite resistant. I was quite hesitant also, that I was telling you that it is not sure that when we are using principal component analysis, it's not necessary that your accuracy might go down. I was quite resisting yesterday in the previous session. So that's the reason I told it's not necessary that if you are taking very less components of principal components, your accuracy should go down or go up, or it might be equal. Principal component analysis is just that it captures, it is used for converting your original input features to new features based on the amount of variation of the data being captured. Based on that, it helps only in reducing your computational time. But as we have already seen, when I write 1 and then with 73% of the variation of the data, original data, we were able to come up with the accuracy which was 0.933. That means that clearly suggests that PC1 is influencing more to your output. That means your predictions are highly influenced, or your outputs are highly influenced by PC1. And when you put PC2, your accuracy is going down by 0.033, right? So it could be because PC2 might be carrying the amount of information, like 22% of the information is being carried, or like 22% of the variation is being captured by PC2, but it might not be that useful in terms of influencing your output. So that was the reason I told yesterday also, when we have input features x1, x2, x3 and x4, and x4 is, say, let's say x4 is x1 plus x2 plus x3. Then how does x4 is influencing your output? It's just a linear dependency of x4 on x1, x2 and x3, right? So that's the reason I told that we cannot comment whether your accuracy will come down with using PCA or it will remain same. Okay, so we cannot comment on that. So let me tell you that with 2, when I'm using 2, it depends on the data also. That's the most important thing. With 2, that means 95% confident, I'm getting accuracy 0.9. But when I'm going with only 73% accurate confidence, my accuracy is 93.3%. It's because PCA is never meant for reducing or increasing your accuracy. PCA is just meant for speeding up your simulation, speeding up your compilation of your code, executing your code. Okay, that was the reason yesterday also I told that you cannot judge whether your R square will increase or decrease when you use principal component analysis. See, here you have already noticed with 73% of confidence, our accuracy is quite high. But with 95%, our accuracy was 90%. That means this 73% of the data which we have captured using PC1, it is quite sufficient to give the same amount of accuracy which we were getting with all the input features x1, x2 and x3 and x4. That itself suggests that instead of running this code with all the input features, we can run with only PC1. Again, make sure the sentences what I'm telling is limited to this data set only. Okay, let me read your next question. So we cannot say this is better, right? So only accuracy would not be a good parametric for comparison. Yes, as I already told, accuracy is not always accuracy. We cannot tell that accuracy is a better measure. We cannot tell that. If I look only for accuracy, we can tell that with 73% information and with original dataset, I was getting same accuracy. So I have never tell that accuracy is a right measure to check for. There are a lot of different parameters, and some of them, if you remember, precision, recall, true positive rate, all the remaining things which we have discussed in our earlier sessions.